In lesson 67, we'll be looking at areas between curves again, but in this case we're going to have equations where they're x equals equations instead of our standard function notation. So as we look here, we have find the area of the region completely enclosed by the y-axis, and the graph of x equals 1 minus y squared. So what I have here first is a graph, and since we're familiar with things when we have y equals, what we did is we went ahead and solved for y, so we could add y squared to both sides, subtract x from both sides, and we get 1 minus x, take the square root, and we have plus or minus the square root of 1 minus x. And so we would have to split this up into two equations. So y equals the square root of 1 minus x. The positive one is this square root function opening to the left because it's like a negative x plus 1, so it's moved right 1. And then you have the flip side of it using this negative. And so we would have to find the area between this graph and the x-axis, and then this graph and the x-axis, and add them together. A couple different ways to think through that. But what we're going to do in this lesson, instead of changing it over to function notation, we're going to go ahead and leave it like this, and instead of finding the area under a curve between the function and the x-axis, we can still look at this as one graph, but instead of us using these little dx change in x's here, this is like our dx, which is the width of our rectangle. The width of our rectangles now will be dy, and the height of our rectangle will be the x value, which is what will be given to us. So x is equal to 1 minus y squared. So we're finding the area between two curves, so we integrate and we do our kind of summing up of our rectangles. So we're going from negative 1 up to 1. And then the height of our rectangles is the x value, so 1 minus y squared, because x equals 1 minus y squared. And then our width is dy. And so we're just going to be integrating this. So we have y minus 1/3 y cubed, evaluated from negative 1 to 1. Now, I didn't mention to find this negative 1 and 1, you want when your x value is 0, so you could put 0 in for x. And you could solve for y, so add 1 to both sides and take the square root, and you get plus or minus 1. And that gives us our values for the indices of the integral. Another way we're familiar with parabolas, so we could have realized they did go through negative 1 and 1 on the y-axis. So now plugging in, we have 1 minus 1/3 minus, when we put in negative 1, so negative 1 minus 1/3 times negative 1 cubed, which is still just negative 1. So we have 2/3 minus, this is negative 1 minus 1/3, or plus 1/3, so this is negative 2/3. So we actually have 2/3 minus negative 2/3, which is 4/3. So the area between those two lines or graphs is 4/3 units squared. So let's look at one more. Find the area of the region completely bounded by the graphs of x equals 3 minus y squared and y equals x minus 1. We're really familiar with this one. This is a line. Y-intercept is negative 1. The slope is 1, so we know the graph of that. We're familiar with this. Oftentimes we would see it in the form negative y squared plus 3. So this is a parabola that's going to be opening to the left, and it's going to be moved to the right 3. So we could sketch those graphs. I have some here already that we can take a look at. So here's what we would have had to do before. We could have left this in y equals x minus 1 form. We could have solved this for y, where we would have those two parabolas again, or two square root functions. And for a lot of the time, you could have done the line minus the parabola, but then once we get to this value here, we have to change it up. So it would end up being somewhat cumbersome to do that. So what we can do, instead of using this option, we could look at making our rectangles horizontal, which again we'll use a dy for that. And so we notice we can do our parabola minus the line, because this is when we do it with the horizontal rectangles, we want to do our rightmost function minus the left function. We usually think higher minus lower, but this we do right minus left. And we want these as x equals. The points are here on the graph, and remember we're interested in the y values here, not what we did before when we were looking at the x values, but we're looking at the y values. So we're going from -1 to 1. It didn't show how to find that, but what you could do is you could take your two equations and use either substitution or elimination to find the points where they intersect. Again, if you're familiar with a graph, you can easily find those points, kind of like the last one. So we want to go the right one, which is the negative y. I just realized I wrote this wrong a while back. This would have been y. Oh, no, never mind. So we have this negative y squared plus 3 minus, well, we want this in terms of x, so we could add 1 to both sides. We get x equals y plus 1. So we're going to subtract y plus 1. And this is dy, because the widths of the rectangles are dy. It's pretty messy looking. Here we go. Let's go ahead and add like terms or whatever we need to do here. So we actually have a negative y squared. We have a 3 minus 1, so we'll have a 2, and then we have this negative y. dy. We can integrate. So this is -1/3 y cubed minus 1/2 y squared plus 2y, all evaluated from -1 to 1. This isn't a lesson on integrating, so we should know how to find this integration as you plug in -1 and 1. So if you work through all of that, you end up getting 9/2. So kind of the main idea of the lesson, depending on the functions that you're finding the area between, sometimes what we want to do is we want to look for the equations in terms of y instead of the equations in terms of x.